As Andrew Ng says, AI is the new electricity. But neurons are good for nothing without the mathematical basis of backpropagation. So the big question is, what's backpropagation? One way to look at it is like tuning the neurons to the rhythm of loss function. Let's take MNIST classification problem as an example. Now here, each 28x28 grayscale image has the label associated with it. What we want to create is a machine that can read digits even if it is written haphazardly. But please understand that no matter how deep the neural network is, ultimately it is nothing but a function approximator. The function between the actual image and the label is learned by a neural network with the help of backpropagation. When the information flows from input to output in neural network, we simply do weighted sum of inputs. This is called forward pass. Think of it like cascaded operations of functions over an input. But the real crazy stuff happens in the backward pass, where we align each weight to the tune of loss function. For this, you require gradients of loss with respect to weight. This is because we want to subtract the weight by the factor of same. This is called gradient descent and is quite common technique in optimization. In this, you subtract the derivative of the function with respect to the weight, and then you get a smaller value of that function. But the problem is that there are millions of parameters in this function. How to find the derivative of loss with respect to each parameter? This can be insanely complex. That's when backpropagation comes into the picture. It is quite similar to the idea of reusability and optimal substructure in dynamic programming. It tells you that look, we should not start from the scratch every time. We can reuse our previous computations. If we can express the gradient of loss with respect to the current hidden layer as a function of the gradient of loss with respect to subsequent hidden layer, then we can avoid the curse of computation. Current gradient as a function of subsequent layer's gradient. For simplicity, let us consider hidden layer H, which has an incoming connection of H1 and H2 and an outgoing connection with H3, H4 and H5 as shown in the figure. Now if you have activation function, we have to split this hidden layer into before activation and after activation. I have expressed this via superscript. Given this, we will try to express 2L by 2H in as a function of 2L by 2H3 in, 2L by 2H4 in and 2L by 2H5 in. In the chain rule, 2H out by 2H in depends on activation function you have used. In the case of sigmoid, it is minus e to the power minus h in divided by 1 minus e to the power minus h in whole square. This is nothing but the derivative of sigmoid with respect to input. In this case, that's h in. In absence of activation, the factor becomes 1. That's because function is just a constant 1 multiplier. Also, do h5 in by do h out is w5 because that's the weight which is connected to h out and h5 in. So now ultimately, we are able to obtain the current gradients based on the weighted sum of the previous computed gradients. At this moment, you can pause the video and ponder over the mathematics. Now to compute the gradients of the loss with respect to W1, the chain rule is as follows. Note that we have dou L by dou H in already computed by the iterative update in the backward pass. To summarize the whole flow, if there is a neural network, in the forward pass we will get the hidden layers values based on forward pass, and in the backward pass you'll have to find the gradients of the overall loss function with respect to the hidden layers based on the equations mentioned earlier. And calculating dou L by dou W is just a single step. That's because we already have dou L by dou H for all the hidden layers. The last step is to change the weight based on this approach. This change is proportional to dou L by dou W. And don't forget to like the video if you found it really helpful. Do subscribe the channel and press the bell icon if you want to receive crazier ML insights in the future.